Welcome to Talk Tensors. This is the deep dive, where we don't just, read the abstract and nod along. We actually dismantle the architecture, debug the methodology, and really analyze the mechanics of the papers that built the modern ML stack.
Right, the real nuts and bolts.
Exactly. And if you are a machine learning practitioner right now, maybe staring at a loss curve that absolutely refuses to converge, or a grad student drowning in open tabs, or just someone obsessed with the engineering reality of AGI, you are entirely in the right place.
It is great to be here. And today, we are doing some necessary archaeology. We're going back to a paper that I think is arguably the most important pre-transformer paper in terms of its pure impact on modern scaling laws.
Yeah, we are setting the dial all the way back to early 2017. The paper is titled Outrageously Large Neural Networks: The Sparsely-Gated Mixture-of-Experts Layer.
I always laugh at outrageously. You really have to appreciate the audacity of that adverb.
It's so rare.
It is.
Yeah.
In academic publishing, you usually get efficient or scalable or maybe robust if they're feeling spicy. You rarely get outrageous.
It sounds a bit like clickbait, honestly, but then you look at the author list and you realize they absolutely aren't kidding. We're talking Noam Shazir, Azelia Mirasani, and the godfathers themselves, Jeffrey Hinton and Jeff Dean. This is the Google brain team at the absolute peak of their powers.
And the use of the word outrageously was quite literal in this context. They were proposing model sizes up to 137 billion parameters that at the time seemed computationally suicidal.
Just completely unfeasible.
Right. For context, most state-of-the-art models in early 2017 were sitting in the hundreds of millions of parameters. They were proposing a 1,000x jump.
Let's actually set the technical context before we get deep into the architecture, because it's important. It's early 2017, the transformer hasn't dropped yet. Attention is all you need is still months away. The dominant architecture for sequence modeling, so translation, language modeling, all of that, is the LSTM, the long short-term memory network.
Yeah, we are still very much unrolling loops over time. But the industry is hitting this massive, undeniable wall, the dense scaling wall.
Let's unpack that for the listener. We knew empirically that bigger models performed better, like capacity, the sheer number of parameters you have, correlates directly with the model's ability to absorb information.
But the catch with dense models is that every single neuron is active for every single input.
Right.
Which creates this brutal linear coupling between model size and compute cost. If you decide you want to make your model 100 times smarter by adding 100 times the parameters, well, you have to pay 100 times the FLOPs for every single forward pass.
Floating point operations, yeah. And crucially, you have to pay that cost at inference time, too. It's not just a training problem. Latency becomes an absolute killer.
Exactly. You couldn't just say, let's make it bigger, without waiting literally years for it to train on the clusters of the time, or needing a small dedicated power plant to run inference for your users. So Shazir and the brain team were looking for a way to break this coupling, and they revisited an old idea.
Conditional computation.
Conditional computation, yeah.
The thesis here is brilliantly simple when you think about it. If I ask you to solve a complex differential equation, you use a very different set of neurons than if I ask you to identify the smell of burning toast. You don't light up your entire neocortex for every single trivial task.
It's biological sparsity. It's biomimetic.
But I want to be clear, this wasn't a brand new idea. Jacobs and his team proposed a mixture of experts all the way back in 1991. And there were several serious attempts in 2013, 2015. So why did all of those fail to produce state-of-the-art results?
It comes down to the hardware. And this is the classic tension we see constantly in AI. You have theory on one side and hardware reality on the other. GPUs are SIMD devices, single instruction, multiple data. They absolutely excel at dense matrix multiplication. They want to do the exact same math on a massive, contiguous block of numbers.
They really like lockstep execution.
Precisely. They want predictability. They hate branching. If you tell a GPU, for this data point do A, but for that data point over there do B, you destroy the parallelism. You introduce what's called warp divergence in CUDA terms.
Right, the threads get out of sync.
Exactly. And the GPU essentially ends up serializing the operations to handle the divergence. So your theoretically highly efficient, fancy, sparse model actually runs 10 times slower than a dumb brute force dense model.
So the real core contribution of this paper isn't just dreaming up the architecture. It's the hardcore engineering realization of conditional computation on modern, highly dense hardware.
Correct. They essentially figured out how to make sparsity palatable to a GPU cluster.
Okay, let's dissect the actual solution here. The Sparsely-Gated Mixture-of-Experts Layer, or MoE. Visually, what are we actually looking at if we map this out?
Well, imagine a standard deep LSTM network. You have stacked layers, one on top of the other. What they do is take an existing layer and replace it with this MoE structure. But instead of one giant monolithic weight matrix that processes every single token, you have a collection of independent subnetworks.
The experts.
Yes, a collection of independent experts.
And in this paper, that number N gets really aggressive. We're not talking about 2 or 3 experts. We are talking about thousands.
Thousands. Up to 131,072 in their absolute largest experiment.
Which is wild. And what is the actual topology of a single one of these experts? Is it complex?
It's surprisingly simple, actually.
Yeah.
Each expert is just a standard feed-forward network, an FFN, with one single hidden layer and a real U activation in the middle. So it's literally just matrix multiply, then real U, then matrix multiply.
Okay, so we have this massive library of thousands of these FFNs sitting there. But the whole point is we aren't running all of them at once.
No, absolutely not. That would defeat the purpose. That's the job of the gating network. This is the manager of the layer. For every input X, which, in this context is usually a word embedding or a hidden state vector passing through the sequence, the gating network receives it and decides which specific experts are best suited to handle it.
Let's get into the math of that gate, because this is really where the magic and honestly the immense difficulty lies. The output Y of the MoE layer is essentially the weighted sum of the selected experts, right? So the equation is Y equals the sum of G of X sub I times E sub I of X.
Yes. Where G of X is the output vector of the gating network, and E sub I of X is the output of the I of expert. The critical piece here is that G of X is highly sparse. For almost all values of I, G of X sub I is exactly 0.
Right, because they use a top K gating logic.
Usually K equals 4 in their main experiments. So out of, say, 2,000 experts, the gate identifies the top 4 best matches, assigns them weights that sum to 1, and sends the signal only to those 4. The other 1,996 experts are completely bypassed. They do 0 compute.
It's so elegant. So you have a model with literally billions of parameters available in the library. But for any given word you're processing, you effectively only pay the compute cost of a very small model. You have officially decoupled capacity from compute.
In theory, yes. It's a beautiful concept. Okay. But implementing that top K selection in a way that actually trains is mathematically treacherous.
Because things like argmax or top K are discrete operations. They are step functions in the math.
And as anyone who is taking calculus knows, you cannot backpropagate through a step function. The gradient is exactly 0 everywhere, except at the sudden jump where it's totally undefined.
So the chain rule just dies.
The chain rule dies. Yeah. If an expert isn't selected by the gate, it gets absolutely no gradient signal. It doesn't know I wasn't selected, so its weights don't update. It can't learn to be better for the next time.
Right, so if I'm expert number 5, and I was the 5th best choice for a token, but K is 4, I get cut. I get 0 gradient. I don't change my weights at all. The next time that token comes around, I'm still just the 5th best, so I starve.
You starve, exactly. It's a massive dead neuron problem on a macro scale. So Shazir introduced what he called noisy top K gating. This relies on a variation of the reparameterization trick, somewhat similar to what we see in variational autoencoders.
Let's walk the listener through the actual equation for the pre-gating score, the HX.
Sure. So they calculate the score as the dot product of the input and the gating weights, but then they add a crucial noise term. The equation is H of X of I equals the dot product of X and WG, plus a standard normal distribution sample multiplied by a soft plus function of the input dotted with a separate noise matrix, one noise.
That's fascinating. So they have a learned weight matrix, WG, for the actual signal, and a completely separate learned matrix, one noise, that literally controls how much noise to inject per expert.
Yes. The network learns its own variance. It learns exactly how noisy it needs to be to explore the space. Then they apply the keep top K function to this noisy signal, and only then do they run a softmax to get the final routing probabilities.
Why does injecting random noise fix the dead gradient problem, though?
It smooths out the discontinuity of the step function.
Right. Because
you are adding Gaussian noise before the cutoff, there is always a non-zero probability that a slightly suboptimal expert might accidentally cross the threshold and get picked.
So forces exploration.
It forces exploration. And mathematically, it allows the expected gradients to flow back into the gating weights, even for the experts that currently rank below the top K. The gate can sort of feel the potential of the unselected experts through the noise distribution.
It effectively turns the hard, sheer cliff of the top K selection into a very steep but fully differentiable slope.
Exactly. It's a brilliant workaround. Without that noise, the gate almost always collapses to a deterministic, rigid routing that ignores 90% of the experts forever. With the noise, you get healthy load balancing and valid flowing gradients.
Okay, so mathematically, we have a differentiable sparse router. In theory, we are good to go. But now we have to actually run this thing on a Google data center cluster. And this is where section 3 of the paper, the implementation details, becomes a literal war story.
Oh, it really is. The shrinking batch problem. This is the exact bottleneck that quietly killed all those previous MoE attempts we mentioned.
Let's explain the physical reality of this bottleneck to the listeners.
So GPUs rely on massive batch sizes to hide their memory latency. Let's say you have a global batch size of 1,024 sentences. For the standard dense LSTM layers, the GPU crunches all 1,024 items in parallel. That gives you high arithmetic intensity.
Meaning the ratio of math operations happening to the amount of memory bytes fetched is very high. The cores are kept busy.
Correct. But then the data hits the MoE layer. Suddenly, the gate takes those 1,024 items and scatters them across, say, 1,000 different experts. By the pigeonhole principle, on average, each expert receives maybe one item.
A batch size of 1.
A batch size of 1 is catastrophic for a modern GPU. You'd end up spending all your time loading the expert's weight matrices from VRAM into the compute registers. You do a tiny microscopic bit of math for that one token, and then you have to throw the waste right back out to load the next expert. The CDA kernel launch overhead alone basically kills your throughput.
So how did they solve this? Because they obviously couldn't just accept a 100x slowdown and publish a paper about it.
They had to write custom infrastructure. They implemented a highly complex hybrid of data parallelism and model parallelism.
Let's clearly distinguish those two for everyone.
Sure. Standard deep learning training is almost always data parallel. Every single GPU has a full, identical copy of the model, and each GPU processes a different slice of the data batch.
Right. You average the gradients at the end.
Exactly. But MoE training in this paper is model parallel. The experts are physically distributed across the cluster. So GPU 1 might hold experts 1 through 100, GPU 2 holds experts 101 through 200, and so on.
So the model itself is physically sharded across the hardware.
Yes, but here's the trick. When the batch of data arrives at a layer, the gating network, which is replicated on every GPU, decides where each specific token needs to go. Then the entire cluster executes an all-to-all shuffle.
An all-to-all shuffle. That's a very specific, very heavy communication primitive.
It's massively heavy. They physically move the activation data across the PCIe bus, or the high-speed network interconnect. So if a word sitting on GPU 1 needs to be processed by expert 500, and expert 500 lives on GPU 5, that specific word vector is shipped over the wire to GPU 5.
And because this is happening for the whole cluster simultaneously, GPU 5 is receiving a bundle of words from all the other GPUs at the exact same time.
Exactly. So the effective batch size for expert 500 isn't just the local items from GPU 5, it's the aggregate demand from the entire cluster. By combining all those routed tokens, they restore a large enough batch size to make the GPU math efficient again.
That brilliantly solves the compute efficiency. But wait, doesn't that introduce a massive network bandwidth bottleneck? You're shuffling the entire massive activation state across the physical wire twice per layer, once to get the data to the expert and once to get the result back.
It does. It introduces a huge latency penalty. And this physical reality completely dictates the design of the experts themselves. To make this whole crazy dance worthwhile, the amount of computation you do once the data arrives at the expert must be large enough to dwarf the time it took to send the data over the network.
Ah, the compute to communication ratio.
Exactly. This is the exact reason why the experts in the paper have such large, hidden layer dimensions like 2048 or 4096. They have to be very fat experts. If they were tiny, shallow networks, the network transfer latency would completely dominate the training time, and the GPUs would just be idling, waiting for data packets.
It's such a fascinating constraint. The physical hardware architecture of the cluster literally dictates the mathematical neural architecture of the model. You simply cannot have lightweight experts because the copper wires between the machines are too slow.
Welcome to large-scale deep learning. Honestly, it's mostly hardcore systems engineering disguised as calculus.
Truly. Okay, there's one more vital control system we need to discuss before we get to the results. Load balancing. We briefly mentioned the rich get richer problem earlier.
Right. Left entirely to its own devices, the gating network will often find one expert that initializes slightly better. Let's call it expert 42, and it just starts sending everything there.
It's a complete routing collapse.
Total collapse. Expert 42 gets all the data, so it gets all the gradient updates. It learns faster becomes tangibly better than the others, and the gate heavily reinforces that loop. Meanwhile, expert 99 never sees any data, gets no updates, and effectively just randomizes.
And from a hardware perspective, you end up with a giant, dense model running on exactly one GPU, while the other 1,000 GPUs in your cluster sit completely idle.
Exactly, which is a massive waste of millions of dollars to compute. So they had to modify the core loss function. They added auxiliary losses to force the network to behave responsibly.
They added two specific terms. Let's start with the first one, the importance loss. The math says it minimizes the squared coefficient of variation of the importance scores.
Let's break down the coefficient of variation, because it sounds intimidating. It's just the standard deviation of a set of numbers divided by their mean.
Right.
It essentially measures lumpiness or inequality in a distribution. If the gate assigns exactly equal importance weights to every single expert, the variance is 0, so the CV is 0. If it heavily favors just a few experts, the CV explodes.
So by adding the squared CV to the total loss, they mathematically penalize the model during backprop if it doesn't spread the importance weights relatively evenly across the entire population of experts.
That's right. It's an artificial pressure to be egalitarian. But importance is just a measure of the continuous weights. You can technically have high importance weights, but very low actual load, especially if you narrowly miss the top K cutoff.
Right, because you only route to the top 4.
Exactly, which is why they absolutely needed the second term, load loss. This term is concerned with the discrete choices. It ensures that the actual integer number of examples physically sent to each expert is balanced.
This might seem a bit redundant to a casual listener, but it's actually about memory safety, isn't it?
It's entirely about memory safety.
Yeah.
If GPU 1 gets 10,000 items routed to it, and GPU 2 only gets 50 items, GPU 1 is going to run out of VRAM trying to build the computation graph, and the entire distributed training run crashes with an out-of-memory error.
Yeah, the dreaded.
Exactly. The load loss is essentially a please keep the GPU memory balanced loss function. They derive a smooth estimator of this discrete load so they can backpropagate through it.
It's just amazing they were taking strict hardware and cluster networking constraints and injecting them directly into the mathematical optimization landscape of the AI.
You have to. At this scale, if the software doesn't respect the hardware literally breaks.
All right, so we've built the machine, we've solved the shrinking batch, we've balanced the cluster load, we've smoothed the discrete gradients with noise. The big question, does it actually work? Let's dive into the experimental results section.
They started with language modeling, evaluating on the 1 billion word benchmark,
which was the standard rigorous data set for the time. Lots of news articles.
Yeah, and they compared their sparse MoE models against the absolute best-in-class dense LSTMs of 2017. Crucially, they strictly matched the computational budget during inference. So roughly 8 million FLOPs per time step for both models. It was an apples-to-apples test of compute efficiency.
And what was the delta in performance?
The 4096 expert MoE model achieved a 24% lower perplexity than the dense baseline.
24% is massive. I mean, in NLP research, we usually pop champagne for a 1 or 2% drop in perplexity.
It was a generational leap. But the true killer stat is the efficiency comparison. To achieve the exact same perplexity as the absolute best dense model they had, the MoE model used only 6% of the computation.
6%. That totally validates the whole conditional computation thesis right there. You really can be significantly smarter without working harder.
Precisely. Then they decided to scale it way up. They moved to the Google News corpus, which is a 100 billion word data set. This is where they pushed the parameter count to that staggering 137 billion number.
The truly outrageous model.
The outrageous one, yeah. And they found that the performance gap between MoE and dense models actually widened as the data set grew. MoEs are absolute data sponges.
Because they have such vast parameter memory, the thousands of experts, they can memorize rare grammatical patterns, edge cases, and nuances that a smaller dense model simply has to discard just to focus on the common core of the language.
Exactly. Which leads us to probably the most philosophically interesting result in the entire paper, machine translation. Specifically, their multilingual translation experiment. This is the one model dream. Typically, you train one specialized model for English to French, a completely separate model for English to German, and so on. In this paper, they trained a single massive MoE model on 12 different language pairs simultaneously.
And how did it hold up?
It outperformed a dense multilingual baseline model on 11 out of the 12 pairs. But the really crazy part, it actually outperformed the dedicated monolingual specialist models on 8 out of the 12 pairs.
That is profound because it implies the model isn't just muddling through and averaging the tasks to be decent at everything. It is actively switching contexts to be a master at specific things.
We believe, and later layer analysis pretty much confirmed this, that the gating network learns to partition the experts by language entirely on its own. It dynamically routes French tokens to a dedicated subset of French experts and German tokens to a subset of German experts.
It's emergent modularity.
Emergent modularity, exactly. It didn't need a human to explicitly label the data and say, hey, this is French, rooted here. It statistically learned that the linguistic patterns of French require a specific subnetwork to minimize loss, and it built that routing traffic accordingly. It effectively evolved a Broca's area for French and a Vernix area for German inside the weights.
That is incredible, and it naturally brings us to the legacy of this work. We're sitting here discussing a paper from early 2017. As we noted, LSTMs are dead. Transformers rule the world. Does that make this paper just a cool historical curiosity?
Absolutely not. The base architecture, the LSTM, is obsolete, sure. But the meta-architecture, the sparsely-gated mixture-of-experts, is the gold standard for modern scaling.
Explain that connection for us.
This specific paper laid the exact groundwork for things like the switch transformer from Fetus et al. In 2021, G-Shard and essentially every massive frontier model in production right now, rumors very heavily suggest that TPT-4 uses a mixture of experts architecture.
And we know for an absolute fact that open weights models like Grok 1 and Mixtral are MoEs. It's in their technical reports.
Exactly. Shazir and his co-authors mathematically proved that you cannot scale densely forever. The heat and compute costs literally kill you. The only feasible way to reach trillion parameter scale effectively is via conditional computation. This paper was patient zero for making that work on real-world GPU clusters.
It's the blueprint.
It is the blueprint. The LSTMs were really just the vessel at the time. The cargo, the sparse gating mechanism were the actual revolution.
However, we should note they were very honest about the limitations in the discussion section.
Yes, they were. They noted that diminishing returns eventually kicked in hard around 65,000 experts. You couldn't just scale into infinity. And the software complexity, distributed MoE training is still notoriously unstable. Debugging a cluster where the active neural architecture changes per token on the fly is a total nightmare.
Yeah, if one node fails, or if the load balancing drifts even slightly out of alignment, the whole billion parameter run just collapses.
It adds a massive layer of fragility to your infrastructure. But as we've seen in the last few years, the AI industry collectively decided that fragility was a price well worth paying for the sheer scale it unlocked.
All right. We have thoroughly dissected the past and contextualized the present state of MoEs. Now, let's look out a bit further to the future.
It's time for the Novel Notions segment.
Yes, it is. And I'll give our standard disclaimer to the listeners. The following ideas are outlandish, highly speculative, and purely for entertainment purposes. Please do not cite us in your thesis defense.
Or do, and tell us how it goes.
Fair enough. I'll start us off. We talked extensively about how the paper uses a completely fixed number of experts. You define n equals 2048 in your YAML config file, and you are stuck with it for the whole run.
Right. It's treated as a rigid, standard hyperparameter.
My notion is what I'm calling the Darwinian expert layer.
Oh, evolutionary deep learning. I like where this is going.
Exactly. Why do we humans arrogantly decide how many experts the model needs before we even see the loss curve? Let the data decide. We constantly monitor the importance metric that they defined over the training epochs. If an expert is consistently ignored by the gate, if its importance drops below a certain baseline threshold for thousands of steps, we just prune it, we kill it, we delete the weights and free up the VRAM.
You literally fire the underperformers.
Ruthlessly. The network sheds dead weight. But conversely, if an expert is constantly capped at maximum load, if the gating network is just screaming to send more data to it but is bounded by the load loss, we trigger mitosis. We clone that expert.
Would you just copy the weights exactly?
You copy the weights exactly to preserve the representation, but you add a tiny microscopic bit of Gaussian noise to the new clone to break the symmetry, and then you let them diverge naturally over the next few epochs.
That is fascinating. So, for example, if you were training on a massive medical data set, the generic general anatomy expert might get completely overloaded, split into two, and eventually differentiate into specialized cardiology and neurology experts organically.
Exactly. The topological structure of the network would physically grow and branch out to match the underlying topological complexity of the data manifold.
You wouldn't need to guess the capacity up front. The model would just expand dynamically until it had enough compute surface area to solve the problem.
Right.
The main engineering challenge there would be the warm start problem. A newly cloned expert is immediately competitive because it inherited good weights. But what about a newly initialized expert if you wanted to inject fresh capacity? It would be garbage, so the gate would never pick it. You'd need some kind of nursery mechanism to force a certain percentage of traffic to the infant experts so they can actually get gradients and learn.
Like a protectionism loss function or a forced exploration epsilon?
I like it a lot. It's a very cool systems challenge.
Thanks. What is your notion for today?
Mine rests directly on the multilingual translation result we discussed. We saw that the model naturally and spontaneously separated languages into distinct expert groups.
Right, the emergent Broca's area.
I call this idea the semantic polyglot. Currently, that kind of deep semantic specialization is treated as a happy accident. I want to make it an explicit mathematical objective.
How do you enforce that?
You add a strong dissimilarity loss term to the overall loss function. You mathematically force the internal vector representations of the different experts to be orthogonal to each other in the high-dimensional space. You actively penalize them for being similar. Force them to be as radically different as possible.
Okay, and then what data set do you train this on?
Everything. The pile, common crawl, Python code, Shakespeare, dense legal contracts, chaotic Reddit threads.
Just the absolute sum of human text chaos.
The theory is that by forcing this strict orthogonality during a massive pre-training run, you force the MoE experts to become pure, distinct semantic primitives. You wouldn't just get language experts. You might get one expert that purely handles Python syntax, another that purely processes human empathy and sentiment, another dedicated solely to logical deduction.
Oh, wow. This sounds like a direct route to interpretability.
That is exactly the goal. Right now, dense LLMs are these massive, opaque black boxes. But if we can map an orthogonal MoE, if I can definitively prove that expert 42 is the sarcasm expert and expert 105 is the math logic expert, I can physically control the model's cognition.
You can perform localized brain surgery on the weights.
Exactly. Is the model hallucinating wild facts? Just temporarily turn down the activation gain on the creative fiction experts. Is the model being overtly toxic or aggressive? Just mute the internet argument experts at the routing level.
It effectively turns AI alignment and safety from a vague behavioral training problem into a literal audio mixing board problem. You just adjust the routing faders.
Precisely. Instead of alignment via RLHF, we achieve control via routing interventions.
I really love that concept. If anyone listening builds the semantic polyglot or the Darwinian layer, please let us know.
Yeah, we definitely want early beta access to that.
Absolutely. Well, let's wrap this up. Outrageously Large Neural Networks by Shazir et al. It proved definitively that the path to AGI isn't just about endlessly piling up more and more dense layers. It's about routing information intelligently through a vast, sparse possibility space.
It taught us that we really don't need to use our entire brain to think a smart thought.
And it reminded us that sometimes the true bottleneck isn't the calculus or the theory, it's literally the physical copper wire connecting the GPUs in the rack.
Always check your network bandwidth, folks.
Check the show notes for the link to the original paper. It is a dense read, but the implementation sections are an absolute masterclass in distributed systems engineering.
Highly, highly recommended reading for anyone touching large models today.
Thanks for listening to this deep dive on talk tensors. Keep your gradients sparse.
And your experts busy. Goodbye.